Right. Here, a teacher demonstrated the behavior of electrons traveling through a graphite. An electron beam was directed through a thin piece of graphite towards a fluorescent screen as shown. Here, we have the electron beam over here and the graphite over here, and the curved fluorescent screens over here. The electrons produce a pattern on the fluorescent screen as shown below here. Right. This demonstration can be used to make conclusions about the behavior of the electrons and the structure of the graphite. State these conclusions. Right. Here you can clearly see a diffraction pattern. So we can conclude from that what electrons are behaving like waves over here. And here you can see that the structure of this diffraction pattern, right? It is regular or it is layered. So what we can tell from this one, the structure of graphite must be layered or ordered or regular, right? And if we are having a diffraction, we all know to have a better diffraction, the wavelength and the gap of the slit uh, should be equal, right? If we are sending some wave like this, if we are having a diffraction, right, what should happen? This gap, and let's call it d here, and this one is lambda, and these two should be nearly equal to have a better diffraction. So what we can tell from this one, the de Broglie wavelength of the electrons is similar to the spacing of gaps between atoms. Because why? The gaps between atoms is acting as they're acting as slits over here, and the de Broglie wavelength of the electrons are acting as the wavelength of the beam, or what we call, yeah, beam, right? So how can we answer for these questions by stating these conclusions? First thing, you should mention what electrons can exhibit wave behavior, right? Or here we can see a diffraction pattern. That's why we can conclude that point. Electrons can exhibit wave behavior. Right? Why? Right? Electrons diffract as they pass the graphite. Or graphite, here the graphite acting as a diffraction grating, right? Electrons diffract as they pass through the graphite. Or either you can write over here what the graphite, the layer of the graphite or thin layer of the graphite is acting as a diffraction pattern grating over here. So here you can clearly see the pattern of the diffraction is a very structured one. So by that we can conclude what structure of graphite must be ordered or layered or regular, whatever you prefer. So I'm going to write here order, right? Then the de Broglie wavelength of electrons wavelength of electrons is similar to the spacing of gaps between atoms. Right? As I told you, here when we're sending something, the lambda should be equal to d, and here the lambda is actually de Broglie wavelength of electron. So if you can write these 4 points, you will get full marks, right? 1 for each. I hope you got the idea. In the part B, they say the electrons were accelerated through a potential difference of 2400 volts before interacting with graphite. Show that work done on each electron is about 4 times 10 to the power minus 16. Right. I hope you remember this equation. What? V equals W over Q, or we write it as W equals VQ. So I prefer this one, right? So we can easily calculate the work done by using this equation. Why? Because here we are sending electrons and they have given us the potential difference. So we just need to substitute our values for this equation. So work done is equal to potential difference is 2400 volts times charge of an electron, right? So it is 1.6 times 10 to the power minus 19 coulombs, right? 10 to the power minus 19 coulombs. So if you calculate this one, you will get what? 3.84 times 10 to the power minus 16 joules. Got it? So 1 mark for this one, 1 mark for the final answer, right? Second one, calculate the maximum velocity of the electron. This is very simple because now we know our work done, right? And we know what that is equal to the kinetic energy at the final moment, right? Okay. It means if I explain that one, here we don't have a kind of, yeah, right? Here the potential difference is 2400. So what we have over here is 2400. Here we have a positive and here we have negative. So if we have one electron over, just for the sake of argument, right, while it is moving towards this positive plate, what happened? It is accelerating. So at this point it will have kinetic energy which is equal to the potential energy over here, right? Or we can tell that is the whole work done, right? Here we have calculated it. So the kinetic energy is equal to this work done, right, on each electron. Work done by this electric field, I hope you remember these things, right? If I explain bit more, right, here we have electric field over here and the work done by this electric field. So our electron is accelerating through these two plates. So the work done on electrons is equal to the kinetic energy, right? Kinetic energy of electrons, right? Yeah. So what we can do, right, here we know what is our work done, and we all know the ek is equal to half mv square, right? So work done is what? 3.8 times 10 to the power minus 16 joules, and our kinetic energy is half times what is the mass of electron? It is 9.11 times 10 to the power minus 31 kilograms times the velocity, right? Velocity v square, right? Here what they're asking is velocity. So if you calculate this one, right, you will get something. I'm not going to, and you have to subject that one and write the answer. I'm directly going to write that one. It is 2.90 times 10 to the power 7 meters per second. So you have right over here 2.90 times 10 to the power 7 meters per second. So what you need to understand from here is the work done on electrons is equal to the kinetic energy of the electrons at this point, right here, right here. Work done by this field, which means the energy, right, energy is giving from this field to the electron, right, the electron. So the energy given by this field to the electron is the kinetic energy at this moment, right here, right. It's like the potential energy over here is equal to the kinetic energy over here. Like if we have some object and it is falling to the ground, here this is the ground, and the potential energy, or what we call gravitational potential energy over here, is equal to kinetic energy over here, right. It's like this. So to find the potential energy over here, that is what we call work done on electrons, right. That is the work done on electrons by this field. So here we have taken it by applying W equals VQ, and that is equal to the kinetic energy at this moment, because this is the energy given by field to the electrons. So we assume that this is a kind of, this is a closed system, not a kind of, it's a closed system, so no energy lost. So if this is the energy given by the field, so that should be equal to the final kinetic energy of the electrons, right. Okay, here the accelerating potential difference was then increased. Explain how the pattern on the screen would change, right. Okay, right here, right, we use two equations, W equals VQ, oh, oh, then W equals half mv square. So if I substitute VQ half mv square, right, because this is the work done, right. I told you this is the energy given, or energy of the system. So here it is work done, or the energy given by the field to the electron, and that should be equal to the final kinetic energy. So we can write it directly like VQ is equal to half mv square. So if we increase, this is the potential difference, not the velocity. Here we have the speed, or the velocity, it is speed, right. uh, if we increase this potential difference, or the accelerating potential, what happened to this v, then v also will be increased, right. I should mention the first point, what increasing the accelerating potential difference would increase the maximum velocity of electrons, right. Increasing the accelerating potential difference would increase what, the maximum velocity of the electrons, maximum velocity of the electrons, right. Here I told you it is speed, right. When you have v square, it is speed, right, because we have neglected the direction when we have taken a square, right. Velocity is a vector and speed is a scalar. So if it is just v, it is vector, right. It is velocity, right. um, Next point, right. Now we know this one. So uh, the next point is what, lambda equals h over p. I hope you remember this relationship. It is what we call de Broglie wavelength, and de Broglie wavelength of electrons, right, is increasing. Why? The momentum is now increasing. Why momentum is increasing? Momentum is increasing because we have increased the accelerating potential. So here, if we increase this one increases, this one increases, potential momentum increases, which means lambda, or de Broglie wavelength, will decrease, right. So because this is inverse proportional with the momentum, so now this has increased, so this is decreased, right. So you had mentioned that one, what, um, right, lambda equals h over p. So what, uh, de Broglie wavelength of electron, wavelength electrons decreases. Then if the de Broglie wavelength of electrons decreases, what happened to the diameter? Here I told you the graphite, right, uh, act as a kind of not kind of act as a diffraction grating. I hope you remember the equation for that one, right? And lambda equals d sine theta, but here in the actual case it should be 2, right? What we call the Bragg's law, but it is not in syllabus, so you don't need to worry about this 2 over here. Just look at it like this way, what we have in our syllabus. um, so what you know is, here supposed, right, if it is moving like this, and this is the what do you call, refracted ray, and let's go, this one is our theta, right? So if we increase this lambda, right, sorry, we are decreasing, we have, right, because we have increased the increase in potential, accelerating potential, so that would cause to decrease in lambda. So if this is decreased constant, this is d also constant, what should happen to our sine theta? That is also decreases, which means sine theta is the angle between the refracted and incident one. So if theta is decreasing, what happened to our new theta? New theta would be like this, right? Sine theta also decreasing, so the diameter also decreasing, right here. So if the diameter was like this in the previous stage, diameter was like this in the previous stage, now the diameter is like this, because sine theta is decreasing. Oh, it's like this. I hope you clear, right? So what you should write over here is, so the diameter of the circles would decrease. So the diameter of the circles decrease, right? So 1 mark for this one, 1 mark for this one, and 1 mark for this one, right? I have given marks on here, it is about 2 marks. So applying this one, right, this one, and which means taking the work done equals this one, and for the final answer 1. And here these two, so using this one, here I have given, and here yeah, you know, you can then 1 mark for each point, that's it.